Welcome to this lecture on inorganic chemistry. Today, we are going to explore a fascinating topic, the ionic character in covalent bonds. As you begin your journey in chemistry, you will quickly discover that the way atoms share electrons is rarely perfectly equal. Understanding this unequal sharing is the key to unlocking why molecules behave the way they do in the real world. Let us dive in. To start, let us build an intuitive understanding of what ionic character actually means. Imagine two children sharing a large warm blanket on a cold night. If both are equally strong, the blanket stays perfectly centered. But if one child is much stronger, they will naturally pull the blanket closer to their side. They are still sharing it, but the sharing is highly unequal. In chemistry, atoms share electrons to form covalent bonds, but they rarely share them perfectly equally. When one atom pulls the shared electrons closer to itself, the bond starts to act a little bit like an ionic bond. This is what we call ionic character. Now that we have a conceptual picture, let us look at the formal definition. The ionic character in a covalent bond is a direct measure of this unequal sharing of electrons. This inequality is caused by a difference in electronegativity between the two bonded atoms. Electronegativity is simply an atom's inherent ability to attract a shared pair of electrons. When two different atoms bond, the more electronegative atom pulls the electron cloud closer, developing a partial negative charge, denoted as delta minus. Consequently, the other atom is left with a partial positive charge, denoted as delta plus. This separation of charge creates a bond dipole. To better understand this separation of charge we just discussed, let us look at a visual representation of a hydrogen chloride molecule. On the left, we have the hydrogen atom, and on the right, the highly electronegative chlorine atom. Notice how the blue electron cloud is not symmetrical. It is visibly distorted, pulled heavily towards the chlorine atom. This gives chlorine its partial negative charge, delta minus, and leaves hydrogen with a partial positive charge, delta plus. The arrow at the bottom, with a cross at its tail, represents the dipole moment vector, pointing towards the negative pole. This visualizes exactly how a covalent bond takes on ionic characteristics. Seeing this distorted electron cloud brings us to an important question. Why does this matter? Understanding the ionic character of covalent bonds is absolutely crucial because it dictates the physical and chemical properties of molecules in the real world. Take water, for instance. It is a covalent molecule, but its bonds have a very high ionic character, making it highly polar. This polarity is exactly why water is a liquid at room temperature and why it can dissolve so many different substances, earning it the title of the universal solvent. Without this ionic character, water would be a gas, and life as we know it would be completely impossible. Now that we understand the importance of polarity, let us look at how we measure it mathematically. The overall polarity of a bond is measured by a vector quantity called the dipole moment, represented by the Greek letter mu. The formula is mu equals Q times R. Here, Q stands for the magnitude of the partial charge that has been separated in the bond. The variable R represents the distance between the centers of the two bonded atoms, which is the bond length. In plain English, the dipole moment is the product of the charge separated and the distance over which it is separated. If the electronegativity difference increases, the charge difference Q increases and the dipole moment goes up. Similarly, pulling the atoms further apart increases R, which also increases the dipole moment. This dipole moment formula we just saw leads us directly to our next mathematical tool, calculating the percentage of ionic character. We represent this percentage with the letter I. The formula is I equals mu divided by mu max, all multiplied by 100. Here, mu is the actual, experimentally observed dipole moment of the molecule, usually measured in units called dBys. The denominator, mu max, represents the theoretical, calculated maximum dipole moment if the bond were 100% ionic, meaning a complete transfer of one full electron had occurred. This formula is essentially calculating a test score for the bond's polarity. It tells us what fraction of a fully ionic bond our real covalent bond has managed to achieve.
Before we move on, let us see this with a concrete example. We will calculate the percentage of ionic character in a molecule of hydrogen chloride. We are given the experimentally observed dipole moment as 1.03 dBi and the bond length as 1.27 times 10 to the negative 8 centimeters. The fundamental charge of a single electron is 4.8 times 10 to the negative 10 electrostatic units. Our first step is to determine the theoretical maximum dipole moment, assuming a complete transfer of one electron. We use our formula mu max equals Q times R. Multiplying the fundamental charge by the bond length gives us 6.096 times 10 to the negative 18 electrostatic units centimeters. Since 1 dBi equals this exact unit, our theoretical maximum is simply 6.096 dBi. Now that we have our theoretical maximum, we can finish the calculation. We apply our percentage formula by taking the experimentally observed dipole moment of 1.03 dBi and dividing it by our calculated theoretical maximum of 6.096 dBi. The dBi units cancel out perfectly, leaving us with a dimensionless decimal ratio. We then multiply this decimal by 100 to convert it into a readable percentage. The resulting value is 16.9%. This physically tells us that the hydrogen chloride bond is primarily covalent, but it has a significant ionic flavor to it, achieving nearly 17% of a fully ionic bond's polarity. So we have successfully calculated ionic character using experimental data. But what if we do not have laboratory measurements for the dipole moment? This brings us to the Harney-Smith equation. This empirical formula provides a highly practical way to estimate the ionic character using only the periodic table. In this equation, I again represents the percentage of ionic character. The symbols chi-A and chi-B represent the Pauling electronegativity values of the two bonded atoms. The vertical bars mean we take the absolute, positive difference between them. Mathematically, this shows that the ionic character scales with both the linear difference and the square of the difference in electronegativity. As the gap in electronegativity grows, the percentage of ionic character increases very rapidly due to that squared term. Now that we have this new formula, let us apply it to a second example. We will estimate the percentage of ionic character in a hydrogen fluoride bond using only electronegativity values. We are given the standard Pauling values, 2.1 for hydrogen and 4.0 for fluorine, which is the most electronegative element on the periodic table. Since we lack experimental dipole data, we rely on the Harney-Smith equation. Our first step is simply to find the absolute difference in electronegativity between the two atoms. We subtract 2.1 from 4.0, giving us a difference of 1.9. This is quite large for a covalent bond, which immediately tells us to expect a very high degree of ionic character. With our electronegativity difference calculated, we can now find the final percentage. We substitute our value of 1.9 into the Harney-Smith equation. First, we multiply 16 by 1.9 to evaluate the linear contribution, which gives 30.4. Next, we square 1.9 and multiply it by 3.5 to evaluate the exponential contribution, yielding 12.635. Adding these two parts together gives us a final estimated ionic character of approximately 43%. This physically means that the hydrogen fluoride bond is nearly halfway to being a completely ionic bond. This high ionic character perfectly explains why hydrofluoric acid has such unique and dangerous chemical properties. We have covered a lot of ground today, so let us summarize the key takeaways. First, remember that no heteronuclear covalent bond is perfectly covalent. They all possess some degree of ionic character due to unequal electron sharing. We learned that we can quantify this exactly by comparing the actual dipole moment to a purely ionic model. Alternatively, we can estimate it using the Hannay-Smith equation and simple electronegativity values. Mastering this concept is a massive step forward in your chemistry education, as it allows you to predict the physical properties and reactive behaviors of molecules in the real world. Great job following along, and keep up the excellent work.